Today is day 3, and this is lecture 5. Title is The Application of Vibrational Spectroscopies in the Studies of Small Molecules. Tomorrow, I will talk about the studies of biomolecules. What is the difference? Molecular weight. Okay? So, the number of vibrational modes is calculated for n atomic molecules and not linear molecule. Then the number of vibration modes is 3n minus 6. So in the case of small molecules, let's consider n is equal to 10, order of 10. Then this number should be close to 30, exactly speaking, 24, but nearly 30. In the case of biomolecules, the number of atoms is large. Accordingly, the number of the vibration mode is huge. So the approach to small molecules and biomolecules must be different. So today's talk focuses on the analysis of small molecule. Okay. So I cannot cover all the area of the studies, but I introduce a few examples of the studies in relation to 3 topics: structure analysis, identification, and some experimental techniques. Okay, I cannot cover all the studies, so this is a typical study. Okay, so one of the representative small molecules that is studied extensively is 1,2-dichloroethane. So layout is somehow changed. So we know there are 2 forms, gauche form and trans form. What is the difference? Direction of the CCl bond is different. In the gauche form, CCl bond is this direction, and the other is in plane. If we see configuration of the atom from this point, then we can set the CC bond in this direction. Then 2 CCl bond should direct this direction. This is gauche form. This is 60 degrees. The other is a trans form. Okay. So in this case, CCl bond, 2 CCl bonds are in plane in this case. If we see from this side, CCl bond should direct upward and downward. Okay, so there are 2 forms. And I explain some examples about this molecule. When we pick up one molecule, we should check symmetry group that this molecule belongs to. A gauche form has a C2 axis along with this direction. C2 axis, when this molecule has C2 axis, let's rotate 180 degrees, or this 2 means 2. So by rotating 180 degrees, it becomes the identical arrangement of the atoms. Okay, if we rotate 120 degrees, what happens? 120 degree, then the configuration does not overlap. So this molecule does not have C3 axis, C4 axis, C6 axis. Okay, this molecule has C2 axis. So by rotating 180 degree, it returns to the original position. We call it this molecule has a C2 symmetry, or this molecule belongs to C2 group. On the other hand, how about transform? This molecule has higher symmetry. So when we watch this description, we can find the C2 axis in this direction. So by rotating 180 degree along with this axis, it returns to the same structure. Besides the C2 axis, it has a mirror plane. By putting mirror, including, so by putting mirror on the plane, including Cl, Cc, Cl, then two H atoms are in the mirror image. Two H groups are mirror image, this side and the back side of this mirror. In this case, we call it, this molecule has mirror plane, mirror symmetry. And in this case, this is so-called sigma H plane. Okay? And this molecule has an inversion center. So, by moving H atom to this position, move Cl atom to this position. So, how can I say? If we multiply the coordinate by -1 and set this origin, then coordinate of each atom return to the same structure. In this case, we have this molecule, we call it, this molecule has inversion center. Okay. So in the case of trans molecule, there is a C2 axis, sigma H plane, and inversion center. In this case, this molecule is classified to C2H group, or we call it C2H symmetry, or this molecule belongs to C2H group. This is a difference between two structures. We know the number of atoms is the same, and probably along with the rotation, these two structures are compatible to each other. But when we describe the static structure, there is a clear difference between the two. And we can calculate the vibration frequency about the transform and gauge form, respectively. So we can prepare this kind of calculated frequency and observation frequency, and we can check these two calculated number and observed number correspond to each other. So we can make sure transform should have these vibrational modes, gauge form has these vibrational modes. So the agreement between calculation and observation ensures the appropriateness of these structures. Okay. So when we want to study the small molecules such as 1,2-dichloroethane, please make sure the vibrational assignment. As far as the number of atoms are small, it's affordable, and we can list all the vibration modes. Okay, it's hopeless if this is a protein that consists of 10,000 or 100,000 atoms. I cannot list all vibration modes. This is a limited number, so please make sure. And after calculating the vibration frequency like this, we should make sure if this calculation is really appropriate or not. One method is to examine the isotope effect. So we have a technique, organic synthesis technique, to label or replace hydrogen with deuterium. In this case, CH stretching vibration is affected because the reduced mass changes by replacing H with D. Accordingly, peak shift should occur. So by performing vibration frequency calculation about this isotope labeled molecule, we can check if the calculation is appropriate. So somehow we can compare the calculated frequency and observation even for the isotope labeled species. So this is the method to ensure the appropriateness of the assignment. So this is the Raman spectrum. So according to the calculation, each mode is assigned to T trans, Gauss, trans, like this. Okay. And in the textbook, you will find the table symmetry about the symmetry operation, and we can say the molecular vibrations that belong to AG group, BG group are Raman active. AU group, BU group are IR active. So the classification to AG or AU, BG, BU is given when we fix a symmetry group. And the we define the symmetry group for the molecular structure. As well, we can define symmetry for about the molecular vibration mode. So we can classify the displacement vector to each group. That is, each molecular vibration is classified to one of the four groups in this case. In this case, not atomic coordinate, but displacement vector is evaluated. Symmetry of the displacement vector is evaluated. So we can classify the vibration mode into four groups, and each group are already known to be Raman active or IR active. In the case of C2 group, classification is only about A and B. So I didn't prepare some detailed explanation about the symmetry operation, but please run another chance. So anyway, we can classify the molecular vibration into some symmetry groups, and already it is known some groups are Raman active, some groups are IR active. In this case, all the vibrations are Raman and IR active. Okay, this gives a hint to discuss the molecular structure. So Raman active mode should appear in the Raman spectrum. IR active mode should appear in the IR spectrum. In this case, there is no selection. And in the case of C2H, IR active is Raman inactive. Raman active is IR inactive. So, briefly speaking, when the inversion center is present on the molecule, then IR active, Raman active, and vice versa. This is so-called the rule of mutual exclusion. So in this page, I explain the importance of the classification of the vibration mode into several groups, symmetry groups. And in the case the molecule has inversion symmetry, then IR active mode and Raman active mode are exclusive. Okay? So it's time to see the experimental result. This is a Raman spectrum, Raman spectrum of 1,2-dichloroethane in the liquid phase and solid phase. This is IR spectrum of the 1,2-dichloroethane in the liquid phase and solid phase. And already we know which peak is assignable to which conformer, trans, gauche, gauche, and trans, gauche, sum, and so on. And when the phase changes from liquid to solid phase, the number of bands decreases. You see, gauche mode is absent. Gauche mode is absent. Gauche, absent. Gauche, absent. On the other hand, trans is here, here. Okay, apparently only vibrational band of the trans conformer appears here. It's also the case gauche mode is absent. Gauche mode absent. Only transform seem to remain in the solid phase. So from this result, if we know the assignment, we can say in the liquid phase, trans and gauche forms coexist, and in the solid phase, only trans form exists. A consistent result is seen in the IR spectrum. In the liquid phase, gauche and trans coexist, and only the trans form exists in the solid phase. So, based on the knowledge of the mutual exclusion rule, we can explain based on the peak assignment, we can explain what happens during the phase change from liquid to solid. Okay, so long time ago, it was believed that the CC rotation along with the CC axis, rotation of the H2Cl group along with the CC bond was free rotation. If that is a free rotation and there is no difference in the energy, the both structures should coexist even in the solid phase, but it was not the case. Then it's possible to conclude there seem to be two forms in the liquid phase and only the transform exists in the solid phase. So this is an example how to utilize Hyper-Raman spectroscopy in the study of the small molecule. Okay, from this result, they excluded the possibility about a free rotation old picture, that the potential energy does not change along with the rotation along CC axis. So this group rotates. This group rotates. It was considered it happens freely. But actually, it should be better to consider three energetically stable structure with a more stable state transform than gauche form. So, due to the experimental result, they concluded there is three minima in the potential curve. Okay, so this is one of the typical examples how to utilize the vibration spectroscopy for the study of small molecule. Actually, I started this explanation based on the knowledge that there is two forms, gauche and trans. But historically, it was opposite. Historically, this observation was made first. At that time, there was no knowledge about the peak assignment. They didn't know what is this. But anyway, there is an observation. Some peaks disappear. Some peaks disappear. So there is no knowledge which peak is which conformer. Then they started to consider why some peaks disappear, why some peaks remain during the phase transition. Then they excluded a calculation of vibrational frequency. And they considered there must be two distinct forms. At that time, there was no name. One belonged to C2H group, the other belonged to C2 group. In that case, there should be some vibrations. And in this case, the vibration mode should be classified to four groups, and Raman active, IR inactive, or Raman inactive, IR active. Then based on this knowledge, they could safely assign each peak to two forms, having a C2H group or C2 group. After that, they named two forms, gauche and trans. So nowadays, we already know there are two forms. But long time ago, they had no idea about two distinct forms. But based on this experiment, to stable structure were identified. This is the finding of the trans and gauche forms. Okay? So the detailed analysis of the vibration mode and peak assignment and classification into the symmetry group helps you to discuss what the meaning of the observed result. And the advantage of the vibrational spectroscopy is that it can be combined with some additional instrument. One is the temperature controller of the sample. So it's possible to wrap a sample cell with some temperature controller, and we can precisely control what is the temperature of this liquid. Okay, so we can measure the effect of the temperature change. What is known? Okay, from the temperature dependence experiment, we see thermodynamic parameter delta H enthalpy change. You know, the different ratio of the population is explained by the exponential function, including the difference in the Gibbs free energy. Okay, if the energy difference is large, then more stable state dominates the state. If delta G is 0, please imagine if this is 0, two forms trans and gauche have the same energy, then the right hand side is equal to 1. So if the energy is equal, population ratio is equal. So N is the number of molecules in trans form, Ng is the number of molecules in the gauche form, and the ratio is given by exponential minus delta G over RT. And you know delta G is replaced with delta H minus T delta S. So this part is separated into two groups. Delta H, sorry. So delta H minus T delta S. So by separating into two parts, T cancels with the denominator, so exponential minus delta S over R and exponential minus H over delta T. Based on this relationship, we can measure the temperature dependence and we can derive delta H. So by plotting logarithmic of NT over Ng against when we introduce log, then this disappears. So it's a function of minus T inverse by so ratio of the Ng and NT-Ng is plotted against 1 over T. Then we should get some linear relationship with which intersection log. So this term comes to intersection. And this term is obtained as a slope. And the ratio of the trans and gauche is estimated by comparing the peak area. So by checking the temperature dependence of the peak area and its ratio, we can derive delta H from this equation. And it is derived to be this number. So they insist when they estimate the population from the peak area, number is this value, delta H is this value. If only they check the peak height, number is somehow different. So difference is peak height indicates the height, but area includes the information of the peak width, and bandwidth changes for the various reasons. So the area should be the better estimation of the number of molecules. But anyway, from temperature dependence, we can get delta H. One more experiment is the electric field effect. Okay, so we can prepare such a cell, and these two are electrodes. By flanking the liquid sample with electrode and measures IR absorption in this case. Again, IR and Raman spectroscopy is easily combined with other techniques. So we can prepare some setup to change the temperature or electric field or some parameters, and we can examine several thermodynamic properties. When we apply the electric field, what happens? Again, the ratio of NT and G is the exponential function of delta G. And by applying the electric field, we attain change in delta G. In this case, delta G gets the additional term. So by comparing the population ratio or the equilibrium constant in the absence and presence of the electric field, we can get the information about delta G. The effect is different from the temperature dependence because the temperature dependence only affects the limited part of the delta G. But in this case, we can affect the delta G directly. And again, this is the result for 1,2-dichloroethane. And already we know there are two forms assignable to gauche, trans, gauche. Okay, then we see what happens when we apply the electric field. Then trans decreased, gauche increased. So from this result, we can expect gauche is energetically stabilized than the transform, and the population increased. It's natural. Gauche has a dipole moment, and this term is related to permanent dipole moment. Transform has no dipole moment. There is no additional term, so there is no energy gain. So only the gauche form got additional energy stabilization and increased the population. And in this case, actually, this is my PhD thesis. When we apply the electric field, not only the population change, but also the orientational change of the polar molecule takes place. And both signals contribute to absorption change, delta absorbance. Delta absorbance consists of two effects. We want to separate two groups, and I want to discuss only change in population. How can we suppress the orientation change? For that purpose, I rotated sample cell. So electric field has a horizontal polarization, and cell direction changes gradually, rotated. Then, when IR light goes to the normal to parallel to the applied electric field, then this is 90 degrees, and result is something like this. Already I assigned gauche increased, trans decreased. But this gauche band does not increase. This gauche band does not respond. It has no response. Then by rotating a cell with respect to applied IR electric field, we can suppress orientational change signal. So by rotating gradually, orientational change component becomes diminished. So actually, at this condition, orientational change contribution becomes 0. In that sense, this result directly shows the equilibrium change or population change. And you see gauche increase, gauche increase, gauche increase, gauche increase, trans decrease. So all the peaks give the comparable response. And from this result, I succeeded in separating the orientational change and equilibrium change, and derived the delta G value to be 111 kilocalorie per mole. This was the first example to affect and determine delta G directly. This was not attainable with other methods. Applying electric field, we can get unique information. One more experiment may be the pressure effect. In this case, they use a special cell, so-called diamond ambil cell. You know, diamond is expensive, but they use diamond because it's hard enough. 2 pieces, so price is twice expensive. But anyway, it's hard enough to protest to high pressure. So this is so-called diamond ambil cell. they put the sample between the two diamonds and put ruby for the reference. Ruby is a reference to indicate the pressure. So there is an established relationship between fluorescence, ruby fluorescence pattern and pressure. So it's possible to estimate what is the pressure in this volume right now. So pressure is the order of gigapascal. So there is no way to put something else. Everything is broken. So this kind of solid is resistant to pressure. So ruby is a good reporter. And pressure dependence gives the information of the delta V. That is the difference of the molecular volume of the trans and gauche form. This is the result of, again, 1,2-dichloroethane. And by increasing the pressure, spectral pattern changes gradually. And there is a relationship between equilibrium constant K, or the ratio of the population between trans and gauche, and pressure. It's a function of delta V, difference in the volume. And analyzing this result, they concluded, they observed that the population of the gauche form becomes larger at higher pressure. So considering the Roux-Chatelier's principle, smaller volume molecule increases at high pressure. So the volume is, delta V is 0.58 centimeter cubic per mole, and gauche form has a smaller volume in the neat liquid. And they also discuss what is the status of the 1,2-dichloroethane under high pressure. It may be amorphous, polymorph, or crystalline, or amorphization again. So by analyzing the peak position and the intensity pattern, we can estimate the status and its pressure dependence. Okay, so I explained a few examples of the structural analysis of the small molecule. So first, please make sure the assignment, and please interpret what is the implication of your data. And you may combine with temperature heater to change the temperature, electrode to apply the electric field, or add pressure to check delta V. So there are many examples to combine the sample cell, develops a new sample cell to measure new physical quantity. So I cannot introduce all the examples. So they are representative examples to derive the thermodynamic parameters. They are the examples of the structure analysis. Also, apart from vibrational analysis, IR and Raman spectroscopy may be applied to the identification. Okay. Yesterday, I explained the intensity pattern of the Raman spectrum is intrinsic to each molecule, so it is called molecular fingerprint. So it's possible to distinguish different molecules by checking difference in the intensity pattern in detail. And because intensity of the non-resonance Raman signal is in proportion to the number of molecules. Sorry. So we can quantify amount of solute molecule. So here is an example of non-resonance Raman signal of glucose in 80% acetonitrile in H2O. Okay, the upper figure indicates the spectrum. Probably you cannot see, but there are two spectra overlapping severely. So let's expand this region. Then we can see the difference between solvent acetonitrile. They are mainly the acetonitrile spectrum. And in this figure, it is chain line. And solid line is the solution spectrum. So the difference in this region corresponds to solute bands difference here. So there are two spectra, solution spectrum and solvent spectrum. Intensity is close to 65,000. Okay? Scale bar is 10,000, right? Then I subtracted solvent peaks, solvent bands from the solution band. The residual should be attributed to the solute, in this case, glucose. And as expected, I detected several peaks. So this peak corresponds to this peak. And you see the height is 100, or the order of 100. As far as we can get a good spectrum, its difference still have a sufficient SN ratio and worth discussing. So please get a good spectrum. That is the first priority. And I change the concentration from 50, 20, 10, 5, 2. And the intensity gradually decreases. Then intensity is plotted against concentration, and there is a linear relationship. Okay? So it means that intensity indicates the concentration of glucose in this case. So in this sense, the quantitative analysis of the solute molecule is possible. In this case, we need to be careful that peak shift does not occur when we change the concentration. So quantitative analysis is possible given that the concentration-dependent spectral change is negligible. Okay, if the peak intensity pattern changes largely upon dilution, it becomes difficult. So every time we need to make sure concentration dependence. And if you find some linear relationship, then you can do the quantitative analysis. And thanks to the unique feature of the intensity pattern, we can distinguish glucose, fructose, maltose, sucrose, or trehalose, or other sugars clearly. That kind of analysis is done as a sugar content analysis in honey. So in this literature, they examine IR spectroscopy, spectrum pattern, intensity pattern of the IR spectrum about the glucose, maltose, fructose, sucrose. And used this fundamental model data to analyze the IR spectrum of honey. They examine 32 honey samples. And by fitting these results to reproduce the observation, and they could determine content of glucose, fructose, sucrose, maltose for 32 honeys. Okay? In this case, partial least square fitting analysis is performed. But anyway, by using this method, we find the content of maltose is high in some cases. Content of sucrose is high in some cases, and fructose and glucose are largely contained in every case. So this is an example of the quantitative analysis of multiple sugars using the vibrational spectroscopy. You see, in this case, we have no knowledge. We do not need to clarify the peak assignment. In this case, they only consider the intensity pattern difference. Okay, in this case, so this is one of the methods to utilize vibrational spectroscopy. Without any knowledge about the vibrational assignment, we may use in this way. Also, recently, many papers are published on machine learning or some computational data analysis procedure. So they analyze the adulteration of honey. Adulteration means honey is a natural product, but it's not an industrial product. So the amount is limited in the market. So it's rather expensive. By adding some impurity or some artificial sugars, they can increase the volume and sell as a natural honey. Okay, then they can get much money. So they want to add, I don't know who is they, but they want to add some sugars, but honey, to, some additional sugar to honey to increase the volume. And these kinds also honey, fructose corn syrup, rice syrup, maltose syrup, blended syrup. Some syrups may be added to honey, but their content is different, distinct from the natural honey. So the difference can be detected on the Raman spectrum in this case, on the vibrational spectrum. So we may check the difference one by one manually, but the easier way is to apply some computational analysis. So in this case, they applied convolutional neural network CNN, and they succeeded in identifying natural honey in the case of 116, and they correctly predicted the addition of LA, so adulteration of these sugars almost perfectly, and irrespective of the added amount of these artificial sugars, this method concluded distinguished them from natural honey. Again, in this analysis, we do not need knowledge about the vibrational assignment. Only the difference in the spectral pattern is utilized. So it's a kind of a convenient method, but as a spectroscopist, I want to know why they can distinguish, at which part they concluded they classified to different groups. So, and I want to know what is the difference, what is the origin of the difference, and relationship with the molecular structure. So, please try to identify what is the vibration assignment. And if you find the difference, please consider why this is different. Then you will get further information about, further knowledge about the object. Okay? But anyway, this is a convenient method to distinguish some adulterated honey from the pure honey using vibrational spectroscopy. Okay. 1 hour? Sorry, so far is two topics: structure analysis, identification, and third topic is the techniques. So I should briefly explain. Have you ever run the measurement of the depolarization ratio? Do you know? For the first time, then I should explain. Okay. So when we irradiate light from this direction and light to the sample from this direction, then the polarization occurs. Electric field is oscillating in x direction. Then we can understand it induces a polarization parallel to the incident electric field. But in most cases, molecule is not a simple harmonic oscillator, but large molecule. So sometimes X electric field induces Y and Z polarization. So electric field along the X direction induces X, Y, Z, and Y direction induces X, Y, Z. Z direction induces X, Y, Z. Okay? And the induced polarization emits the scattered light along with X direction, Y direction, Z direction. Polarization along with X, Y, Z emits the light, scatters light along with X, Y, Z. I mean, even if we irradiate the polarized light, scattered light is not only this component, but also has a component of having a different polarization. This is measured like this. So let's irradiate the sample from the bottom. So polarization in this direction, and it goes to the sample. Okay. So this is X polarization. If X polarization induces the polarization along with X axis and it emits the X scattered light, then this polarization is conserved. So the scattered light should become this direction. So this is so-called parallel component of the scattered light. If we irradiate a polarized light and scattered light has a different polarization based on this consideration, then the scattered light excited with X polarization may have a different rotated polarization. This is so-called perpendicular component of the scattered light. Okay, so the Raman scattering is sometimes accompanied with a change in the polarization. And the ratio of the parallel component and perpendicular component is the parameter so-called depolarization ratio. how largely the polarization changes. This parameter indicates that feature. And this is the electric field defined in the laboratory frame. Alpha is the parameter in the molecule fixed frame. Polarization is accordingly defined in the molecule fixed frame. Okay? So the consideration is somewhat complicated. And alpha defined in the molecule fixed frame has 9 components. When we separate tensor alpha, Raman polarization tensor alpha into 3 parts like this, then it is shown that the sum of the components of the diagonal part or symmetric part or anti-symmetric part, sum of the components, sum of the square of the components are independent of the framework. So this value is not affected by molecular fixed frame or laboratory fixed frame. It's a convenient quantity. And this is so-called rotational invariant. Irrespective of the rotation of the XYZ axis, this quantity is always constant. So this is a laboratory frame. This is molecule frame. This is molecule frame. But irrespective of the framework, molecule or laboratory frame, these numbers are always constant. It is shown. And the depolarization ratio as a ratio of the perpendicular to parallel intensity is related to these parameters by this equation. And further, when we measure spectrum under the non-resonance condition and electronic state is not degenerated, then a term becomes negligibly small. Then rho is approximately expressed with this equation. So you may check this table later. But in the case of diagonal matrix, G0 is finite value, GS, GA are 0. Symmetric, GS has a finite value. Anti-symmetric matrix, GA has only GA has a value. And importantly, these 2 lines. When vibration mode belongs to the totally symmetric vibration, then the polarization ratio becomes the number between 0 and 0.75. If the vibrational mode is non-totally symmetric vibration, it becomes 0.75. So measurement of this number is useful to ensure the peak assignment. if this is a totally symmetric vibration or non-totally symmetric vibration, so the result is different. So we can ensure if the assignment is good or not. In that sense, this is important experiment. So here is a result example of result of CCl4. This is parallel component of the Raman scattering. This is a perpendicular component of the Raman scattering. Parallel component has the same polarization with the excitation beam. Perpendicular component has the rotated polarization of with respect to the excitation beam. And you see the intensity pattern is quite different. In particular, this peak is absent in the perpendicular spectrum. In this case, it corresponds to the result rho is equal to 0. And rho is equal to 0. And this supports an idea that this peak is assignable to this vibrational mode, and this is totally symmetric vibration. And accordingly, just a moment. This peak is assigned to this vibration, and this is totally symmetric vibration. So we expect the polarization should be in this range. And in the observation, it was 0. So it's consistent with the idea that this mode is assignable to this vibration, and this is totally symmetric vibration. On the other hand, in these modes, the polarization is calculated to be 0.75, and it clearly indicates they are non-totally symmetric vibration. So rho is useful to characterize what is the vibration mode. This is sometimes polarized mode, and this is sometimes called depolarized mode. Well, this is an experiment to ensure your peak assignment. So it may be useful in some cases. Okay, next is explanation of the course. So we are talking about how to utilize vibrational spectroscopy. And now I am talking about some experimental techniques. One of the experimental techniques to record the Raman spectrum is coherent anti-Stokes Raman scattering, so-called pulse. The Raman scattering is measured with single excitation beam, okay? But in the case of cars, they use two beams having different intensity or electric field intensity E, different angular frequency omega 1, omega 2, and different wave number vector K1 and K2. Yesterday I explained K1, so this is the polarization direction, but in this case, please forget that definition. K1 and K2 is completely different direction. So they introduce two beams. Okay, if they introduce two beams at this configuration, crossing configuration. Okay, this is E1, this is E2. Do you see beat in this region? Okay, there is a beat. So due to the interference, some beat corresponding to the difference correspond to the difference of the free angular frequency. The fringe occurs, beat occurs. And just that kind of fringe induces the molecular vibration in the same phase. I prepared media unavailable. Okay. So I prepared some movie that all the vibration occurs together in the same phase. That is, the molecular vibration occurs in the coherent manner, having the same phase due to the interference or fringe between these two beams. And the coherent vibration of the molecule interact with E1 again. Then, as a consequence, a Raman signal appears in the new direction. This is a Karsh signal. Karsh is one of the nonlinear spectroscopy, and the reason is that signal intensity is not linearly in proportion to the incident beam power. Signal intensity is in proportion to E1 square E2. And frequency, signal light has a frequency of 2 omega 1 minus omega 2. And the propagation direction of the signal is given by 2k1 minus k2. So the mechanism is completely different from spontaneous Raman scattering. Advantage of the Karsh is that signal is strong. It's a beam. It propagates to one direction. Okay, this is in contrast to the Raman signal. So excited. Raman signal go to everywhere, but Karsh signal only propagates this direction. So when we collect the signal and detect by the detector, we can gather the signal only in this solid angle. But in the case of Karsh, all the signal appears in this direction. So by setting the detector here, we can detect all the signal intensity. That's why signal is strong. Also, sometimes spontaneous Raman signal is interfered by strong fluorescence background. Raman intensity is much weaker than fluorescence, so it becomes difficult to analyze. Fluorescence also happens in this experiment and goes all the direction. Again, Karsh signal only go to this direction. So fluorescence may also propagate to this direction, but setting aperture here, and most of the fluorescence is cut by this aperture. So it is almost fluorescence-free measurement. It's an advantage. On the other hand, there is a drawbacks because of the intense electric field of the light. It damages the sample. It can damage the sample. And this method is not available for the turbid sample. And this is not available if the light excitation beam is absorbed. This is the energy diagram. So in the case of Karl's measurement, omega 1 minus omega 2 correspond to the fringe at the overlap point of the two beams. If the fringe frequency matches with the vibration frequency of the molecule, then this state interact with omega 1 and emission of the Karl signal occurs very frequently. If there is no vibrational levels, then this process does not occur so largely. So this is the vibration frequency. If the fringe frequency matches, then signals become strong. And from this figure diagram, you see the energy of the Karl signal is larger than omega 1. Okay? And its difference is energy difference between omega 1 and Karl corresponds to the vibrational frequency. That's why this is so-called anti-Stokes Raman. The name is coherent anti-Stokes Raman scattering. That's it. Okay, and Karl's, I explained some advantage of Karl's, but this is not perfect method. Okay, Karl's signal can be measured within 50 milliseconds. It's very fast. So it's an advantage. But this is the raw signal of the Karl's signal. What is this? Baseline seems to be here, and there seems to be negative signal. Actually, the low Karl's signal does not correspond to Raman signal. It's because intensity is obtained as a consequence of interference between the non-resonant background and molecular vibration. Okay, so some additional effect. Background component interferes with the beat of the Karl signal and makes the spectral pattern quite complicated. So there is an established method to correct this contribution of the background component. After correction, baseline becomes 0 and all peaks becomes positive. And this spectral pattern is almost the same with the non-resonant Raman spectrum. This is measured by taking 5 minutes. This is 50 milliseconds. So quite fast method. But one point must be taken care of. that is the contribution of the non-resonant background. We need to somehow compensate this effect. And I said Karst is a fluorescence-free method. This result clearly shows the advantage of Karst. When we measure Raman spectrum of ethanol, pyridine ethanol solution, then detection of the Raman signal is quite difficult due to the large fluorescent background signal. Actually, we cannot say where is a peak. It looks a peak, but that's all. Using Karst, we get a green spectrum, and it's very clear, fluorescence-free. So Karst signal is not affected by the pyridine fluorescence, and in such a case, this is a very good method to record the Raman spectrum, to record the vibrational spectrum. Okay. Okay, Hyper-Raman spectroscopy. Okay. Only 3 slides. So, sorry, I took 1.5 hours. So, Hyper-Raman spectroscopy is, I explained different methods from Raman spectroscopy. Raman spectroscopy is a one photon excited method, excitation and one photon scattering. And signal gives the information of the molecular vibration. Okay? Hyper-Raman spectroscopy is a 2-photon excitation process. So nearly twice the energy is scattered during this process. And Hyper-Raman scattering is related to the hyperpolarizability. This is similar to the reason the Raman scattering is correspond to the polarizability. One of the advantages of the Hyper-Raman spectroscopy in the study of the small molecule is that it has a unique selection rule. Okay, in the case of benzene, it belongs to the high symmetry group. And by checking the symmetry table, you will see A2U and E1U modes are IR active. Red group are IR active. And Raman active is Gerard vibration, green group. And it was well-known fact that both IR and Raman spectroscopy cannot detect the remaining part. These vibration modes have not been detected, and it was so-called silent mode. And using Hyper-Raman spectroscopy, it has a different selection rule, and Gerard mode are Hyper-Raman active. It means all the vibrations that belong to Gerard group, blue box, are detected in the Hyper-Raman spectrum. And with a 1064 nanometer excitation, they measure the Hyper-Raman spectrum of benzene, and actually they clearly detected the silent mode. Okay. So this is the unique information obtained only from the Hyper-Raman spectroscopy. Also, in the case of N-acetyl methylacetamide intensity pattern of the Hyper-Raman spectrum is different from Raman and IR. So in this case, amide 3 mode is the strongest. This is in contrast to the Raman spectrum, where sorry, I cannot say what is this peak. But this is amide 1. And in the IR spectrum, amide 1 is the strongest. So the intensity pattern is different. So there is a possibility that the Hyper-Raman spectrum is suitable for the analysis of the amide 3 band. Okay, and it is known amide 3 mode is related to the peptide main chain structure, so it must be convenient for the protein structure analysis. That is the expectation. Okay, so this is all for this morning lecture.